Now, he says, I don't even have to remind you that, in fact, speciation has been observed and that genetic evidence proves beyond doubt the concept. It really depends how you're going to define evolution. And I've defined it in two major categories. There's horizontal and there's vertical. And if you want, and you need to get technical here, because in science today, normally science should be very precise and rigorous in its definitions, but perhaps one of the most sloppiest definitions in science today is the word evolution. It can be defined as something like the variation within different flavors of, I'm speaking for the layperson to understand here, but a gene codes for a protein, and you can have different varieties of the same gene. We'll call them varieties. In science, you might call them alleles, but let's just call them varieties. And so one of the definitions, a mainstream definition, say, for example, when I took genetics at the University of Waterloo, is evolution is defined as a variation within these different varieties of the same gene in a population over time. And that happens. We can reproduce that. We can, and in science, you don't personally have to reproduce it. If you observe it happening in nature, then it's been reproduced. You've observed the reproduction of the theory. So yes.
So like you can look at a house cat and a tiger and say, okay, there's a lot of similarities between these things. Were they the same at one point? Do they have a common ancestor? That kind of thing.
The question is common ancestor. And so to precisely define the difference between horizontal and vertical evolution, it needs to be a lot more rigorous, because I don't know what the genetic difference is between the house cat and a tiger, but you can define it such that you can then determine whether there is a common ancestor here. And the definition, I would define horizontal evolution as it doesn't require no statistically significant increase in genetic information. So the genetic information in the genome or the DNA of a life form has an amazing ability for a huge amount of variation, but no new information is required. No statistically significant levels of information. But if you want to evolve something a lot more different, you're going to need an entirely, usually not just one novel gene. You're going to need a lot of totally new genes that code for totally new stable folding functional proteins. Because the minimum ancestor might have, say, 285 genes, and a lot of life forms today might have 15 or 20,000 or even more genes. So somehow you have to account, if you're going to have vertical evolution, for where do these genes come from. And that's where you could start doing experiments, for example, even computational simulations. And when we do those in the actual lab experiments, we find out that just to code for one average gene requires so much information that we can actually quantify, that if you're going to do it through evolutionary processes, the universe will literally, the last star will burn out before it happens anywhere in the universe. That's how difficult it is to encode for an average protein. But if you got intelligence in the thing, well, we're already building artificial proteins, simple, mind you, but artificial ones. So the moment you have a mind coding software is easy to produce. You withdraw the mind, now you have a problem. So the items that he talks about, speciation, well, you can define, like speciation, depends how it's being defined here, is no problem at all if you're going to define it such you don't need any more genetic novel genes to code here. You're just going to work with what you already have. That's horizontal evolution. And I would define that as no significant additional genetic information is required.